Hello, everyone. Welcome to Physics 212. This is Lab 3, so video lecture on Lab 3. And in this lab, we're going to discuss measuring the acceleration due to gravity using what's called the ball drop experiment. And also, we will do it using a simple pendulum. And then we're also going to look at projectile motion, which, again, we will analyze data that I have collected for you. And there is a really good simulation that I'll have you guys collect some data, and then we'll analyze that data as well. Okay, so let's start with measuring the acceleration due to gravity using the ball drop apparatus. So as you guys know, right, the acceleration due to gravity is the acceleration experienced by an object, right, some object that's dropped near the surface of the Earth. We're assuming there's no air resistance. So that means all objects are going to have basically the same acceleration, right, if we neglect air resistance. And it's around 9.8 meters per second squared. Or if we use CGS units instead of SI units, it's going to be around 980 centimeters per second squared. So the goal for this particular lab is to measure that, that number, that acceleration, which we typically call G. Okay, so here is the apparatus that we're going to use to measure it. And I have a link. You guys want to make sure you watch the video where I show you like how I actually collected the data. Okay, so it's a quick little video just describing how I actually collected the data using this instrument. So what it is you have a ball dropper, right? So there's like a little marble here. Then we have a photo gate that's going to be placed at 15 centimeters below that ball dropper. And a second, so that's, we're going to call that photo gate A. And we have a second photo gate called photo gate B that's placed at some distance below the first photo gate. Actually, we're going to vary this. So these are going to be, there's going to be 5 different conditions. Think of this as delta x 1, 2. So it's the position or the displacement from the first to the second photo gate. So that's where the 1, 2 comes in. So this is going to be 10 centimeters below, then at some point it'll be 20 centimeters below, and then 30, 40, 50, right? So this photo gate's going to keep moving lower and lower and lower. In terms of the terminology for the time, this delta T01 is the time it takes the ball to fall the first 15 centimeters, right? So from the ball dropper to the location of that first photo gate. And then delta T12, this is going to vary depending on the condition, but it's the time it takes to go from the first to the second photo gate. So the main idea is actually really straightforward. Remember that in order to calculate average acceleration, it is the change in velocity over change in time. So if I have an estimate of the velocity at the second photo gate, which we're going to call VB, and I have an estimate of the velocity, how fast it's moving when it passes that first photo gate, VA, and I know the time it takes to go from the first to the second photo gate, which I'm calling delta T12, again, 1, 2 meaning from the first to the second photo gate. Then if I simply compute VB minus VA, change in velocity, over delta T12, the change in that time, that's going to be my average acceleration. But in this case, we know that that acceleration is constant, right? So that's this equation right here. So VB minus VA is my change in velocity, my delta V, over delta T12, the time it takes to go from the first photo gate to the second photo gate, right? From photo gate A to photo gate B. That's my average acceleration. But in this case, the average acceleration is G, right? It is the acceleration of any object as it falls near the surface of the Earth. So that's all we're going to do to compute G. We're going to measure the change in the velocity at those 2 photo gates divided by the change in time that it takes to travel from one photo gate to the second photo gate. Okay, now initially what we need to do is we need to calculate the time for the ball to fall the first 15 centimeters. We want to measure that delta T01. Think of 0 meaning the location of the ball dropper, and 1 is the location ultimately of photo gate A when it's at 15 centimeters below. So the initial setup is slightly different than the general setup. Like this is more of the general setup. And the initial setup, we have the first photo gate right before the ball triggers it. And the second photo gate is going to be 15 centimeters below it. And we need to do that so that we can compute this time, delta t01, okay? So I did this for you, right? I did several ball drops, and these were the times that I recorded. So I did 5 trials, and I got these particular values in seconds, right? So it took around 0.1557 seconds, right, for my first trial for the ball to fall from the first to the second photo gate. So the first question that you have to work on for your lab report is you want to compute the average delta T01. So what is the average time for that ball to fall the first 15 centimeters? Okay, so just given those data values, compute the average. Then I also want you to compute the percent experimental accuracy. So let me remind you how to do that. I'll do a similar example just to remind you. We talked about this in lab 1, but you may have not seen this in a little bit. So let me remind you how to compute that particular value. Okay, so I'm just gonna make up some values. Let's say that you found delta T01 to be these 5 values: 0.1531, 0.1528, 0.1545, 0.1539, 0.1563. Okay, and I want to compute the percent experimental accuracy of delta T01, right? I want to get a measure of the variability, right? It's the precision. So remember, the first step is you average these values. So if you average these, right, add them up and divide by 5, you're going to get 0.15412. But then remember, you always have to round to the resolution of the instrument, which in this case is 4 decimal places. So I need to round this to 1541. So this is my average delta T01. All right, so that was the first step. The second step to computing percent experimental accuracy is I need to find now all the absolute deviations. Right, absolute deviations. So I have the second column. These, by the way, are in seconds. These also will be in seconds. So remember how to do that, right? It's how far each data value is away from the mean. So you subtract the mean, but you make it always positive. So you take absolute value. So in this case, this first one would be 0.0010. That would be the first absolute deviation. Then you would look at the second value, right? So it's 0.1528. How far away is that from 0.1541? So you subtract, make it positive, you're going to get 0.0013. For the next one, it's going to be 0.0004, then 0.0002, and then 0.0022. Okay, so those are all my absolute deviations. The next step, remember, was to average those, right? So if you average them, it turns out you're going to get 0.00102. And then again, you round to the resolution of the instrument. So if I round to the resolution of the instrument, I'm going to get 0.0010. So this was my average absolute deviation. Okay, and then finally, remember the last step now to find percent experimental accuracy. So percent experimental accuracy for delta T01 is I take my average absolute deviation, so that was 0.0010. I divide by my average value of delta T01, so 0.1541, and then times 100. If you do that in this case, you're going to get around 0.65%, which is great, right? It's less than 1%. So there's very little variability, right? Remember, the lower the percent experimental accuracy, the better, the less variability that you have. Okay, so that should give you a good idea of how to compute that value. Okay, so again, question 1, find the average delta T01, and then find the percent experimental accuracy for delta T01. And make sure you show me those calculations, right? All right, then, then we have the main setup. So now photogate A will be moved so it remains permanently 15 centimeters below the ball dropper. And B is the one that varies, right? At first, it'll be, actually, you can see the conditions here. At first, delta X12 is 10 centimeters. The distance between two photogates is 10 centimeters. The second condition, it'll be 20 centimeters and so on. So this photogate will start 10 centimeters below photogate A, which means it'll be 25 from the ball dropper. Then it's going to increase to 20 centimeters below A, which means it'll be 35 from the ball dropper and so on. Okay, so that photogate is going to move down. So what we did here, or what I did in terms of the data, again, you can watch that video to see how I collected this data, was I found 3 different values. I found the time that it took, I'll start with this one, delta T12. That's the time it took to go, I do the ball drop, and it's giving me the time it takes to go from the first photogate to the second photogate, right? So that's delta T12. I also found delta TA and delta TB. So what is delta TA, delta TB? Well, delta TA is the time it takes the ball just to pass through photogate A. So it's the time it takes the diameter of the ball just to pass through that first photogate. That's delta TA. And then delta TB is very similar. It's the time it takes the ball just to pass through B. So the time it takes the diameter of the ball just to go through B. Okay. So all those values are in the table. I did 3 trials for each of these conditions here. All right, so question 2, what you guys have to do is, in this case, you want to simply average these values. So average these 3 values, right, from the 3 trials, and make sure that you round to 4 places, right, because that's the resolution of the instrument. So you're going to compute all those averages. You don't have to show me the average computations, just fill in that table, and remember to include this table into your lab report. Okay, question 3. Now, we're going to do a plot, right? So using Pascal capstone, we're going to plot position versus time. But the time that we want here is the total time from the ball dropper to the second photogate, to photogate B. So if you look back at the picture here, right, delta T, the total time, is from the ball dropper all the way to the second photogate. So how do I compute that? Well, I need to know the time that the ball took to fall the first 15 centimeters. That's delta T12. And we have that, right? We have that average. In fact, that average, it was right in that first table that we solved in question 1, right? So that average you guys have. And then you can add that average to delta T12, but remember, delta T12 depends on the condition. So if I want the total time for condition 1, then I'm going to take this average, the time for the first 15 centimeters, delta T01, and I'm going to add the average from here, delta T12, for that first condition. Then if I want delta T for the second condition, I'm going to take the same value, the time for the first 15 centimeters, so that'll be the same for all these cases. And now I need to add the delta T12, but the one that corresponds to the second condition, right? This average, and so on. Right, so that'll give you the total time from the ball dropper to the second photogate, to photogate B. Okay, so then what you're going to do is you're going to plot delta X, which is position, versus delta T, versus time. So you might be very careful with this, right? You want time on the x-axis and position on the y. Make sure you also, even though it's not included in the table here, make sure you also include the 0.00 when you do this plot. And the question is, what is the shape of your graph? So do this plot and then answer that question. What is the shape of your graph? Okay, so you have to think about this, right? Let me go back to the iPad to show you this. Okay, so again, we want to plot position on the y and that was in centimeters, versus time, and remember it was the total time, right, from the ball dropper to the second photo gate on the x. Make sure you include 0, and the question is, what does this look like? Well, think about it, right? This is an object that is accelerating, so its velocity is increasing. So that means the slope of the position versus time graph must be increasing, right? So if the slopes are increasing over time, think of downward as being positive, right? We're calling the downward direction positive. So the slopes are going to be increasing over time. So this should look something like this. So let's say these are my data points. Something like that, right? It's going to be a parabolic graph or a quadratic function. So something like that. Okay, so when you do this plot, you want to do a quadratic fit, and it should look something like that. Where the slope, if you look at the slopes here, so at first it's like 0, right, starting at rest, then it's increasing, increasing, increasing. Remember, these slopes represent the instantaneous velocity at each of those times, and that velocity must be increasing. And it's increasing at a constant rate because we have constant acceleration. So your position versus time graph should look like that, should be quadratic. Okay, so once we've done that, we can move to question 4. This is sort of the main question. Remember, the whole idea was to calculate g, right? The experimental acceleration due to gravity. So in this table, it turns out that you have many of these values already. So these are your 5 conditions, right? The location of that second photo gate relative to the first photo gate when it increases from 10, 20, 30, 40, and 50 centimeters. And this first column here, or really the second column, I guess, is the average delta TA. And then this one is the average delta TB, and then the average delta T1, 2. Well, you already have those values, right? You already computed those values back in question 2 in this big table. So you just need to record them again. So this is the average delta TA for the first condition. This is the average delta TA for the second condition, for the third condition, and so on. This would be the average delta TB for the first condition, for the second condition, and so on. So those 15 values, you're just recording again in this table, okay, in these columns right here. Now, what is VA? Well, VA was the velocity right at photogate A, right? And remember, VB is our estimate of the velocity right at photogate B. So the question is, how do I compute those velocities? And it turns out that in general, right, you can think of a velocity as being the change in position over change in time. Well, in this case, the change in position is the diameter of the ball. So change in position is the diameter of the ball. And then the change in time is the time it took that diameter to pass through the photo gate. So to compute VA here, you're simply going to use the diameter of the ball, which is 1.90 centimeters, divided by this particular time, right, which is your average delta TA. Then to get the next one, it'll be 1.90 centimeters divided by this particular time, and so on. And actually, because photogate A doesn't move at all, these values should be very similar to one another, okay? I believe they're actually quite high too, like 180-ish in terms of centimeters per second. right? And actually, these are the equations right here. D is the diameter of the ball. We're going to use 1.90, so 1.90 centimeters. VB, same thing, diameter of the ball, but now divided by delta TB. Now, these values, of course, are going to increase, right? Because the location of photogate B is becoming lower and lower and lower. So the ball is going through it much faster as it gets lower and lower and lower. So you should find that these values are increasing. And then finally, what we really want to compute here is the acceleration due to gravity, right? The G, so G experimental. So to do that, now we plug into that general formula where it's going to be VB minus VA over delta T12, and that'll give you G experimental. And what I would like you guys to do is when you do G experimental, just round it to the nearest whole number, right? So no decimal places. Round all these to the nearest whole number. Okay. For velocities and stuff, actually the times will be still to 4 decimal places. For the velocity, you can maybe go to like 1 or 2 decimal places, but for G, just round to the nearest whole number. So you're going to compute the average, once you get all your G's here, and in theory, they should be the same, right? Because it's a constant. Now, they won't be exactly the same. It's an experiment. There's going to be some variability. So I want you to compute the average. So this is question 4. Compute the average G. Again, round to the nearest whole number, so no decimal places. And then compute the percent experimental accuracy. So I gave you this other column so you can find all the absolute deviations. And remember, accuracy is going to be the average absolute deviation divided by your average G times 100, right? That'll be the percent accuracy. And then finally, compare your value. So your experimental value is the average. Compare that to the gold standard of 980. So you're going to compare to 980. And that will give you the percent experimental error. Okay? So we'll compare them by computing a percent experimental error. All right, now it turns out there's another way that we could compute G. We could plot the final velocity, VB, at the second photogate versus the total time. Remember, the total time was from this column right here, delta T, the time it took to go from the ball dropper to the second photogate. So if you look at this last table here, this is question 5, you already have these total times. You can just copy them down again from the previous table. Again, this comes from this table right here. So it's these 5 values. And then you already have the VBs. That comes from this table. So these 5 values. So you're just going to copy them down again so that you have those values. And then you want to do a plot of VB versus delta T. Okay, so let me switch over to the iPad to show you like what this ideally should look like. And I would say in this case, don't include 0, 0. In theory, you should, but it doesn't really matter. And I think it'll come out slightly better if you don't include 0, 0. So plot VB versus delta T, but don't include 0, 0. So let me show you that. Okay, so again, we're plotting velocity which is in centimeters per second. This was your VB, right? Versus time in seconds. And remember, this was your total time, delta T, from the ball dropper to the second photogate. We know that the velocity of the object, of the little marble, is increasing, right? It's increasing. And we know it's increasing at a constant rate because that constant rate of increase is the acceleration, and it should be constant. It should be equal to G. So what you should find here is that when you do this plot, it should look linear. Again, we're not going to plot 0, 0, but plot all your other points. You want to do a linear fit through all the data. And remember, when you do a linear fit, it'll give you the slope value. And the slope is really important, right? What does it represent? Well, the slope represents the acceleration of that ball, but the acceleration is g. So the slope is really another estimate of g, right? And it'll have the correct units of centimeters per second squared. So you're going to do that plot on Pascal capstone, and that slope should, in theory, be equal to g. Okay, so once you've done that plot, then I want you to compare your experimental value, that's the g that you got from the slope of that graph, compare it to the accepted value of 980 again by computing a percent experimental error. And again, make sure you show me this calculation, include these tables, and make sure you include all the graphs as well, right? So we have to include a second graph as well. Okay, the next part, we're gonna measure g a different way. We're gonna measure it by recording the period and length of a simple pendulum. So what we're going to do is we're going to use the same simulation that we used in lab 0. Remember lab 0, we looked at a simple pendulum. So we're going to use that same simulation, and here's the basic idea. It turns out the period of a simple pendulum, remember the period is the time for one oscillation, is given by this formula. It's 2 pi times the square root of the length of the simple pendulum divided by g. Well, I can rearrange this equation, right? I can solve this equation for g. So if you do a little bit of algebra, you'll find that g is equal to 4 pi squared L over the period squared. So if we know the length of the simple pendulum and we know its period, we can calculate g. So it's another way of calculating g. So all you really need for data here is you need the time for 10 oscillations, right? So you're going to do exactly what you did before. Again, in lab 0, I give you 5 different lengths. I want you to put the pendulum at, and you want to record the time for 10 oscillations. Let me just jump over that simulation just to remind you how to do this. Okay, so remember, here is the pendulum. So we start the pendulum. You can just choose intro, that'll be fine. We don't need the ruler. Remember, you do need the stopwatch. Generally, you want to bring the stopwatch kind of over by the play button here or the pause button. And then the length, remember it's the slider, will control the length. So I think I wanted at 0.2 is the first one, so I'll just do one of these. Displace it by 20 degrees again will be fine. And then it's going to oscillate back and forth, right? So let me stop this. I'll start the timer. I'll set this to be 20. Hit play, and then remember you have to hover over the stop button because you want to count the time. In this case, we're going to do 10 oscillations. So I'll start it. 1, 2, 3, 4, 5, 6, 7, 8, 9, stop. So 11.20 seconds. That's the time for 10 oscillations when the length is 30 centimeters, right? So you want to do it for each of those lengths, for 20, 30, 40, 50, and 60 centimeters. Okay, so just like lab 0. All right, so let me go back to that, to the handout. Okay, so now that you have the time for 10 oscillations, how do you compute the period? Well, remember the period is the time for one oscillation. So if you just divide these values by 10, that'll give you the period. So you have the period for each of these lengths. Okay, so now actually we can calculate g, right? By using this formula here, 4 pi squared L over t squared, we have L, we have t. We can compute g for each of those 5 conditions. Just like before, when you do g, when you compute g here, round to the nearest whole number. Don't put any decimal places. For the time and the period, that's okay. You could have like 2 decimal places, but for g, just make it a whole number. And then I'm asking you guys to compute basically the same 3 things as before. I want you to find the average, right? So this is question 6. Compute the average g, again, round to the nearest whole number. Compute the percent experimental accuracy. So I gave you this other column so you can figure out all your absolute deviations, your average absolute deviation. And then finally, compute the percent experimental error where you compare your experimental value of g to 980, right? And that'll be the percent experimental error. Great, so that's it for measuring the acceleration due to gravity. The next experiment that we're going to look at is projectile motion. So you can think of projectile motion as basically two-dimensional motion of an object that's near the Earth's surface. And let me jump over to the iPad to kind of show you this in general, like what this looks like. It's basically going to be this picture, but I'll do it out on the iPad. Okay, so projectile motion. So let's say we have an object and it's launched at a particular angle at a particular velocity, right? And I'll say at a particular height as well. So let's say there's an angle theta and the velocity is v naught. So that's its launch velocity and its launch angle, right? It would be theta. And what's going to happen? Well, we know that it's going to look, the path is going to look something like this, right? It'll like rise to a peak and then come back down like that, right? Hit the ground over here somewhere. Extend the ground a little bit. Now, one thing that you typically do with a projectile problem is you immediately compute the initial velocity in the x direction and in the y direction. So to do that, you project this velocity vector onto the x-axis. So this piece right here, this component is the x component. I'll call it v naught x. And I project the velocity onto the y. And this would be v naught y, right? So those are the two components of that initial velocity. Now, the motion in the x direction, if we assume there's no air resistance, right, in the x direction, and we know that there's no forces acting on the ball or the object, whatever is being launched in the x direction, then that means the acceleration in the x direction is 0, which means the velocity is constant, right? So whatever I had to begin with, right, whatever the length of this v naught x is, it's going to stay the same throughout the motion because the x velocity at any point is going to be constant. So I'm going to draw these, try to draw them at the same length, even at the peak there. These are all going to be the same length. And then right before it hits, it'll also be the same length. In the y direction, we do have a force acting, right? We have the gravitational force, the weight of the object. It's acting downward. So in the y direction, the motion looks like free rise, free fall motion. So initially we have a large, right? There's a large positive velocity in the y direction. Here it'll be still positive but smaller. So maybe something like that. Here still positive but smaller. At the very peak, there's no velocity in the y, right? It's all in the x, nothing in the y. And then after the peak, it'll be small negative, then more negative, and so on. Maybe something like that. Okay, so you can think of projectile motion as consisting of two motions: constant velocity motion in the x direction and free rise, free fall motion in the y direction. If you put those together, then you have the motion of a projectile. Now, there's one important horizontal displacement that I want to talk about here as well. So like this distance, this is a horizontal displacement, right? But there's a very important one, and it's the one that's defined to be from the point of projection, so right here, to a point on the path that's at the same elevation as the point of projection. So this distance, this horizontal displacement, is called the range. Okay, and one of the big things that we want to investigate in this lab is how does changing the angle of projection, so if I change this angle theta, how does that affect the range? Well, it turns out there's an equation for this, right? The range so let's just call it R. It depends on several things. It depends, as you might expect, on how fast you launch the ball, what that initial launch velocity is. So it turns out it's V naught squared times the sine of 2 theta. So it depends on the angle in sort of a complicated way, right? Sine of 2 theta. And it also depends on how strong gravity is, right? So it depends on the acceleration due to gravity. So it's divided by G. So like if we made V naught larger and we held everything else constant, the range would increase. If I held V naught constant and the angle constant and I decreased G, well, the question is, how do you decrease G? Can't really do it easily on the Earth, but let's say you brought the whole experiment to the moon where G is like 1/5 the value. What's that going to do? Well, if I decrease G, I'm going to increase the range again, right? So things will go a lot further on the moon. I think one of the astronauts, was Alan Shepard, I believe, demonstrated this by hitting a golf ball on the moon, right? And the range was much greater than it would have been on Earth because G is so small. Okay, so let's go back to the handout. Okay, so before we actually get into the lab itself and the experiment, I want to talk about one more thing. What happens if an object is projected horizontally? So the angle of projection is 0 degrees, right? It's not at some general angle, it's just at 0 degrees. So it's at some height, right? You think about off of a building or something, and it's projected horizontally. So let's say we want to figure out the position, the X and Y coordinates of an object at any time after it's launched. So how can I do that? Well, I know that the object is undergoing constant acceleration, right? So if I write the general formula for constant acceleration for the horizontal motion, I can write it like this. The final position, the X, is equal to the initial position, right, which is like right here. We're going to call that 0, plus the initial velocity in the X direction times t, plus 1/2 ax t squared. This is just your kinematic equation for constant acceleration, right? In this case, in terms of the horizontal motion or X direction. But we can simplify this quite a bit in this case, right? We know that it's starting at 0. We're calling the initial position in the X 0. So this is like 0. We know that the initial velocity in the X is the entire launch velocity, which we're calling V naught, because remember, it's being launched at 0 degrees, right? It's being launched horizontally. It's all in the X direction. So V naught X is V naught, the entire velocity. And then because there's no forces acting on the projectile in the X direction once it leaves, the acceleration in the X direction is going to be 0. So if I plug all these conditions into this equation, this simplifies to X, the X position, is equal to V naught times the time. Okay, so you get this simple kinematic equation, right? Constant velocity in the X direction. Now, if we turn to the Y direction, so this is the general formula for the Y direction, right? Very similar, except I change everything to Y's. So Y equals Y naught plus V naught YT plus 1/2 AYT squared. But we can simplify this. Remember, the initial position in the Y direction is that height H, right? So it's this height H right here. So you can think of this point as having coordinates 0 in the X and H in the Y. So Y naught is H. What's the initial velocity in the Y direction? It's 0, right? Because remember, the projectile is being launched horizontally. Like none of that vector is in the Y direction. It's all in the X direction, right? So there's no component in the Y direction. It's all in the X. And then what is the acceleration in the Y? Well, that's negative G, right? Because it's acting down. It's G, acceleration due to gravity, and it's negative since it's acting down. So this equation simplifies into the Y position is going to be H minus 1/2 GT squared. Now, if we solve this equation for when Y equals 0, so again, if we go back to the picture, Y equals 0 means this position right here, right, when it hits or right before it hits the ground, that is going to give us the time of flight, right? So if we set Y equals 0 in this equation and we solve for t, that's going to be the time it takes to go from it being launched to hitting the ground, right? So we call that the time of flight of the ball. So we're going to need that for later in the experiment. So I computed that for you, and you find that the time of flight is the square root of 2 times the height, right? So it's the height of the gun or the height of the building, depending on whatever, in our case, it'll be the height of the gun. So the barrel is a little bit over the lab bench, right? So the height of the gun or the launcher, or it could be like a building, right? If it's something that's being launched off a building. So it's twice the height divided by g and in square root. That's going to be the time of flight of that particular object. In our case, it'll be the time of flight of the marble. Okay, so in the first part of the experiment, and you guys should really watch the video on how I collected this data, so make sure you do watch that. I have a launcher, right? A spring-loaded gun, a launcher. And I measured the height of the gun above the table. So this is the height of the gun above the table. And then I also had a landing platform. So the ball is launched, it hits the landing platform, and I measured the displacement, the horizontal displacement from the edge of the gun to the landing platform. And this is the data I got. So this is the horizontal displacement of the ball. And then I had a photo gate that was triggered when the ball launched and when it hit the landing platform. So think of it, the landing platform as being like right above the table. It stopped the timer. So I'm getting the time of flight, right? Because I'm getting the time it takes from when it's being launched to right when it hits the table. So this is the time of flight that I recorded, the 5 values. So all I want you to do in question 7 is compute the average height, right? So that's the height of the gun, the ball above the table, right when it leaves the gun. I want you to compute the average displacement and then the average time of flight. Now the goal for this part of the experiment is to compute the velocity in 2 different ways, right? And then we'll compare our results, compare our velocities. And then later, we'll compute the horizontal displacement in 2 different ways and compare our results, okay? Again, make sure you watch this video because it'll make more sense if you kind of see what I'm describing with the gun launching the marble and it hitting the table or hitting the landing platform. Okay, so question 8 is compute the time of flight using that equation, that kinematic equation that we derived. So T equals 2 times the average height, right, of the gun divided by G. We're going to use CGS units for this lab. So remember, G is 980 centimeters per second squared. And then if I want to compute the velocity now, well, that's just going to be the horizontal displacement. So that's the average from this table here. So that'll be delta X average, right? Divided by this time of flight. So I want you to use that time of flight. Okay, sorry about that. There were some technical difficulties here with my mouse. So as I was saying earlier, one way of computing the velocity is to take that average horizontal displacement, like how far the ball went horizontally, divided by the time of flight, and we're going to use this equation to calculate the time of flight. Okay, so record your values in here. So this is going to be the time of flight, and the velocity is going to be the second row here. Now, question 9, a different way, another way to calculate the initial launch velocity, and again, if you watch my video, you'll see this, is you can attach a photo gate right to the launcher at the end of the launcher, and then we can record the time it takes the diameter of the ball to pass through that photo gate. So as soon as it leaves the launcher, it passes through the photo gate. And if I take the diameter of the ball and I divide it by the time it takes to pass through the photo gate, that's going to be my launch velocity. So it's just a different way of computing the launch velocity. So in this case, for the diameter, we're going to use 1.90. For the time it takes to pass through the photo gate, 0.0052. So then you can compute the launch velocity the second way, right? And that'll be in centimeters per second. By the way, this is very similar to earlier when we found the velocity at photo gate A and photo gate B during the ball drop, right? We did the same thing. It was a diameter of the ball divided by the time it took that ball to pass through the photo gate. So same exact idea. Question 10 is simply to compare your two different methods for computing the initial launch velocity. So you have the predicted value is the one from question 8. The experimental is the one from question 9. And you want to compare them by computing a percent experimental error. Remember, when you compute percent experimental error, right, it's the difference, absolute value, so you just make it positive, divided by the predicted times 100. Now, question 11, it turns out there's a couple of different ways that we could compute that horizontal displacement, right? How far the ball went horizontally. So one of the methods is simply the average from the table. Remember, I collected this data for you guys. So I found all those values, how far it went when it hit so when it's launched to when it hits the carbon paper, it leaves a mark, and I measured all these values. So this is the horizontal displacement. So that's one method, right? Just the average of those values is going to be the horizontal displacement. Another method is we could calculate it if you rearrange the velocity equation, right? Remember, velocity is displacement divided by time. I could rearrange it so I have displacement, horizontal displacement, is velocity times time. So the question is, which velocity and which time do I use? So to compute this value, and we're going to call this the predicted value, we're going to use the velocity from question 9, so the experimental velocity from question 9, right, when it passed through the photo gate, times, and then the time here is going to be your average time of flight from the table. So the V0, the velocity, is whatever you got from question 9, and the T here is a time of flight, the average, right, from the table here. And that will give you a displacement, right, horizontal displacement. We'll call that our predicted horizontal displacement. For the horizontal displacement experimental, you're simply going to use the average from this table. So if you average all those values, that's going to be your average horizontal displacement. And then they should be similar. So we'll compare the two by computing a percent experimental error, right? So just like before, find the difference, right? Make it positive, and then divide by the predicted horizontal displacement times 100, and that'll be your percent experimental error. Okay, so that whole first part was simply to figure out the launch velocity using two different methods, and to figure out the horizontal displacement using two different methods. That was it. Now we're going to get into the main part of the experiment. And again, make sure you watch my video because I show you how I collected this data. It's a short video. Here is where we want to vary the launch angle. So we're going to vary the angle. Right? 0, actually at 0, the range we know is 0. I'll explain that in a little bit. But then we're going to vary at 15, 25, 35, 45, all the way up to 90 degrees. And we're going to see how that affects the range. So what I did was I collected 3 trials, right? I had a landing platform that had carbon paper on it, and I launched the marble, it left a mark, and I measured the distance from the mark to the edge of the launch gun. And these are the values I got for each of those angles. And I did 3 trials for each of these angles. So what I want you to do for question 12 is simply calculate the averages, right? So average the 3 trials. Then what you're going to do is you're going to do a plot. you're going to plot range versus angle. So range will be on the y-axis, right? And basically you're going to plot your average range. Your average range versus angle, and angle will be on the x-axis. Right? So let me show you what this is going to look like. Because when you do that plot, it turns out it's going to be like a sine curve fit. And we want to locate the peak of that curve, the peak of the curve fit. And the reason why we want to do that is we want to find the maximum range. So experimentally, we're going to find the maximum range. And we also want to find the angle at which it occurred at. Okay, so let me show you how that works. Okay, so again, we want to do the graphs in Pascal Capstone. So let me give you, let me show you an example graph, because this one's a little confusing. We have to locate the peak of that curve. So the usual, right, classic templates, do the upper left-hand icon. For the X measurement, I want it to be angle. And units are degrees. You can just spell out degrees, or if you want to, if you hold the Alt key down on your keyboard and you type in 248, it should give you a degree symbol when you lift up the Alt key again. If not, just type in degrees and that'll be fine. And then for the Y, we want range. So this will be range, and then that's in centimeters in this case. All right, so remember the angles were 0, 15, 25, 35, 45, 55, 65, 75, and 90 degrees. And the range at 0, of course, is going to be 0. And then let's say I'm just going to make up some data. Let's say this is the data I got. Remember, you guys will have to use your averages right from the table. Let's say this is my data: 20, 33, 38 centimeters, 42, 39, 31, 22, and then at 90 degrees, it's 0 again. Okay, so on the x-axis, I'm going to choose angle. On the y, I'm going to choose range. It kind of looks like a sine wave, right, or part of a sine wave, so that's good. Let's get rid of this line connection. So remember, you hover over data point, right-click, uncheck show connecting lines. And then for the fit here, what you guys want to do is you want to do a sine fit. So click on the fits, and you want to choose this one, sine. Okay. Now, this question is going to ask you for what is the maximum range, experimental, and what is the angle at which it occurs at. You don't want to use your original data points. After you do the fit here, to answer that question, you want to find the peak of the curve. So you want to find just below that point. You want to find that, the peak of the curve right there. So how do you do that? That's when you use this icon right here that's like a coordinate tool. So if you click on coordinate tool, you can do add coordinate tool. And we need to do one thing. So we're going to click on it and then right click it and go to tool properties, coordinates, and I need to adjust this so that the snap to pixel distance is 1. So I'm just going to decrease that to 1 and hit OK. Then I'll have finer control when I move this. Okay, it won't just jump to one of my data points. So now I'm going to slide it to the peak of the curve. So right about there. So that would be the peak of the curve. I'll make sure I put a title in here. So this is range versus angle. And notice when you bring that coordinate tool to the peak, it gives you the coordinates, right? So it's giving you the angle, 45.14 degrees. And in this case, it's giving me my maximum range, which is 41.41 centimeters. So this value right here will be my maximal range experimental, and this will be the angle at which it occurs at. Okay, and when you print out, when you copy and paste this graph into your lab report, it'll keep those two values. So you'll have both of those values there. All right, great. So that's definitely what you want to do for that particular graph. So let me go back to the lab handout. Okay, so once we found those values, the maximum range experimental and the angle at which it occurred at, which I'm calling the optimal angle experimental. Then I can finish answering question 13, right? The optimal angle theory should be 45 degrees, right? 45 degrees is going to give you the largest range. So you're going to put in your value here that you got from your graph. Our case, it was 45 point something, I forget what it was. And then compare the two by computing a percent experimental error. And in question 14 is going to be to do the same thing for the maximal range. So the maximal range experimental comes from your graph, right? Whatever that highest value was when you found the peak of your curve. And in the max range theory, you can calculate by using this formula, but we know that the angle is going to be 45 degrees, right, at which the max range will occur. 2 times 45 is 90, and sine of 90 is just equal to 1. So this formula simplifies to be V naught squared over G. So the question is, what do you use for V naught? What do you use for G? Well, V naught, I would use your velocity from question 9. So it was your experimental velocity, so from question 9. And in G is just 980 centimeters per second squared. So that'll give you a range in centimeters, and that's going to be your maximum range theory or theoretical. And then finally, compare these two by computing a percent experimental error. And remember, you always divide by the one that's not experimental. So in this case, I'm calling it theory, but that's the same as like accepted, predicted, gold standard, theory. They all mean the same thing. All right, now the last part of the lab is using the simulation. So I'm going to have you collect some data using a projectile motion simulation. So in particular, right, I'm giving you the same angles, actually slightly different here, I guess. Let me go back to this one. So this one I start at 15 degrees. It turns out we have to start at, just because of the simulation, we have to start at 25 degrees. So I want you to collect the range information for each of these angles, right, and fill in this table. So let me show you how to use that simulation. Okay, so here's the simulation, right? We start it. You can just use the intro, that'll be fine. Now we want to do a couple of things. We want to start, we want to set the height of this to be 0. I'm going to bring this down to 0, so it's like launching from the ground level. And then to vary the angle, right, the smallest it can be is 25, and then you can just click on this and you can go 30, 35, 40, all the way up to, I guess we want to do 65, right? So 0 is going to be 0, then we're going to do 25 all the way up to 65. So all the way up to here. So you set the angle, and then we want to set the speed, the launch velocity, to be 18. Let me just double check to make sure that's correct. Yes, 18. So I'll just click on this, so it's 18. And then to fire the object, actually right now it's a pumpkin. Let's change that. We can change it up here. Let's change it to a cannonball, okay? Even though there's no resistance, it shouldn't really matter. To fire the object, you just press this red button here and it fires it. All right, so now what we want to do is we want to find that horizontal displacement, which is the range in this case, right? Because it's launched from the ground level and it lands at the same elevation, lands at ground level again. So this horizontal displacement is really the range. So how do we measure that range? Use this tape measure here. So if you drag this so that the beginning is right there, and then I can drag the end of the tape measure to where it hits, something like that. And then you can just read off this answer here, and it gives it to you in meters. Okay, and you do the same thing for each of the angles. So 45 should give us the furthest. And you would measure that one and so on. So from 25 degrees all the way up to 65 degrees. All right, so once you have all those values, right, so you've collected all the data, Then you're going to plot range versus angle again using Pascal capstone. So angles on the X, ranges on the Y, just like before. You want to do a sine fit, and then you want to use that coordinate tool to locate the peak of your curve. And it's basically the same questions I asked for the real experimental data. So same thing for the simulation. Compare the optimal angle experimental to the optimal angle theory, which is 45, right? By computing a percent experimental error. And then compare the maximum range experimental to the maximum range theory, which you can compute, right? Remember, it's V squared over G. But now remember that V naught is 18. We set it to be 18 in the simulation, and we're using SI units now. So G is no longer 980, it's 9.8. Okay, and then you can compare those two by computing the percent experimental error. All right, then I just have one more thing I want you to do with the simulation. So using the simulation, we're going to set the bullseye target to be 20 meters from the base of the cannon, right? Keep the height of the cannon at 0 meters. And then with the angle at 25 degrees, what speed should the cannonball be fired to hit the center of the bullseye? And then if it's at 45 degrees, what should the correct speed be to hit the bullseye? And you're just going to fill in the table with your answer here. So you're kind of just playing with the simulation to figure out, you know, what combination, like what speed do you need for these angles to such that the cannonball travels 20 meters. So its range is 20 meters. So actually, let me show you that real quick. Okay, so here's the cannonball again. By the way, you can clear everything by pressing this yellow button with the eraser on it. It clears all the projectiles. You want to move this so that it's 20 meters away. And then you're going to do this at 25 degrees and then 45 degrees. So you're just going to play with this, right? You're going to kind of play around with the initial speed. Let's say, you know, let's say we think it's 22 meters a second. So I launch it. Nope, that's way too much. So I have to decrease it. Let's say it's 20. Launch it. Still too much. And if you keep playing around with it, eventually you're going to find a correct speed such that it hits the target, right? Directly in the center of the target. Then do the same thing for 45 degrees. Figure out what launch velocity, what speed you need so that it hits the target, right? And you're just going to write down those values. All right, great. And then that's it, right? So that's it for this lab report. So the usual, right? You guys will work in groups. One person will submit it on Brightspace. Make sure you have all the tables, all the calculations, all the graphs. Make sure everything is included. And then I will grade it and get it back to you. Excellent. Thank you.